Hello, in this video we're going to examine what happens when the zero vector is included in the set of vectors, and the theorem that we're going to prove says the following. Let V be a vector space. Any set of vectors that contains the zero vector is linearly dependent. Okay, so let's look at a proof. So let's assume that capital V is a vector space. And let's pick some vectors coming from that vector space. So let's consider the set of vectors which contains the zero vector along with some vectors v1, v2, all the way up through v sub m. And we'll make a note that the v sub i's, those little vectors, come from our vector space. They are elements of capital V. Okay, now, by definition of linearly dependent, we know we have a linearly dependent set if there exists non-zero c sub I such that the following equation holds. So let's take a look at this equation. So let's examine C1. Let's call it C naught times the zero vector plus C1 times V1. That'll just help with our subscripts. C2 times V2 plus all the way up through CM VM. So let's examine this equation, and we know that if we can find C sub i's not all zero, then this is a linearly dependent set. So here comes the punchline. Let C naught equal 1, and let the C1 through C2 all the way up through CM, let those coefficients be 0. And so what this says is that, go back to our equation, we have 1 times the zero vector plus 0 times V1 plus 0 times V2 dot 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 all the way up through the mth term. And that certainly is, those are certainly coefficients that satisfy that equation, and you could say by properties of vector spaces. And so this shows that there exists C sub i's not all zero that satisfy the equation. Namely, if we let C naught be 1, that certainly satisfies the equation. Oops. And at this point, we can conclude that by definition of linearly dependence, this shows that the set is linearly dependent. So therefore, our set of vectors 0, v1, v2, etc., is a linearly dependent set.